In this video, we are going to do the final revision on carbohydrates. Now, what are carbohydrates? Carbohydrates are polyhydroxy derivative. Carbohydrates are polyhydroxy derivative of aldehyde and ketone. They are polyhydroxy derivative of aldehyde and ketones. Okay, now one is the aldehyde functional group. The aldehyde functional group is ROC double bond OH, and the ketone functional group is ROC double bond O and what R. Are we getting it? So all carbohydrates have three major functional groups. We have the hydroxy, that is why I say polyhydroxy derivative of what? Aldehydes and ketone. We have the hydroxy functional group, the OH, and then we have the ketone functional group, which is this ketone, and then we have the aldehyde functional group. Now, the ketone functional group and the aldehyde functional group combined together are called a carbonyl group. They are called a carbonyl group. So we can say that carbohydrates consist of the carbonyl group and then the hydroxy group. Now, having defined carbohydrates, let us talk about the classification of carbohydrates. Classification. Now, carbohydrates are classified in, or based, let's say they are classified in two ways. One, based on the functional group present. Based on the functional group present. Based on the functional group. And two, based on the number of carbons. Okay, so they are classified into two, based on the functional group present and based on the number of carbon. Now, based on the functional group, we have two. From here, we already said that carbohydrate has two basic functional groups, which are the what? Aldehyde functional group and the what? Ketones. So based on functional group, we have what is called the aldose. That is, if it has the aldehyde functional group. And then we have the ketose. That is, if it has the ketone functional group. So based on functional group, we have two types. We have the aldose and the ketose. We have the what? Aldose and the ketose based on functional groups. Is that understood? Now, the next one is based on the number of carbons. Based on the number of carbons. Now, based on the number of carbons, carbohydrates are classified as, based on the number of carbon, they are classified as trioses. That is, if they have 3 carbons. Trioses, if they have 3 carbon. Now, let me do something here so that it will be easy. We have number of carbon, name. Then if it is an aldose, what will be the name? If it is a ketose, what will be the name? So let's look at number of carbon. If it has 3 carbons, almost all of them we are starting. The simplest carbohydrate of biological importance start from 3 carbons. You should take note of this question because it's usually asked. What are the simplest carbohydrates of biological importance? They are the ones that have 3 carbons. And they are called the trioses. The names based on number of carbons, they are called the trioses. Now, if it is an aldose, it is called glyceraldehyde. If it's an aldose, it's called glyceraldehyde. While if it is ketose is called dihydroxyacetone. Dihydroxyacetone. So number of carbons, if it is 3, you call it trioses based on number of carbon. Based on carbon, number of carbon, you call it trioses. That means it has 3 carbons. Now, if it is an aldose, you call it glyceraldehyde. While if it's a ketose, you call it dihydroxyacetone. Now, if it is 4 carbon, they are called as the name implies, we have tri, then what? Tetra. You call it what? Tetrose. Now, if they has 4 carbons, I mean, if it is an aldehyde, what do you call it? If it's a tetrose, if it has 4 carbon and it's an aldehyde, you call it. So this one, tetrose, if it's an aldose, you call it an erythrose. Then this one you call it erythrolose. Erythrolose. Then for 5 carbon sugar, you call them erythrolose or erythrolose. Trulose. Then number 5, pentose. Now if it's an aldose, you call it ribose. While if it is ketose, you call it ribulose. Ribulose. Then number 6, we have hexose. If it's an aldose, you call it glucose. While if it is a ketose, you call it fructose. Then we have number 7. We have we have heptose, 7 carbon sugar, and if it is an aldose, you call it pseudoheptose, and if it's ketose, you call it pseudoheptulose. Heptulose. So these are the classification of carbohydrate based on the number of carbon sugar, or based on the number of carbons. Now let us talk about the types of carbohydrates. Types of carbohydrates. Let's talk about the types of carbohydrates. So let's look at classification of carbohydrate based on the monomeric unit. Classification or types. Now we talk about 1, monosaccharides. Types of carbohydrate. If you want to classify them based on the unit, the subunit, we have monosaccharides. 2, we have disaccharide. And 3, disaccharides. And 3, we have polysaccharide. Now, under polysaccharide, in some cases, we have oligosaccharide classified as polysaccharide. Sometimes the polysaccharide, you have oligosaccharide classified under them. So basically, if you want to classify this now, we'll now say there are 4 types, which are 1, monosaccharide, 2, disaccharide, then we now have oligosaccharide, and 3. Supposed to be monosaccharide, oligosaccharide, and polysaccharide. Okay? No disaccharide. 3. Now, some cases, oligosaccharide is classified as what? There is disaccharide in oligosaccharide. Okay? So basically, now if you want to classify them, you now say there are 4 major types, from monosaccharide to disaccharide to oligosaccharide and what? Polysaccharide. But oligosaccharide is classified as, disaccharides are classified as oligosaccharide. Is that okay? So what are these carbohydrates? The monosaccharide, disaccharide, oligosaccharide, and polysaccharide. Let's take monosaccharide. Now, monosaccharide, they are like the simplest forms of carbohydrate. The simplest. They have the general formula of normal glucose formula, C6H12, then what? O6. This for glucose. Normally, all carbohydrates have general formula of CN, H2NO, which in most cases is given as CH2O bracket N, where N is the number of carbons. So if we have 3 carbons here, to be C3, H6, and what? O3. Are you getting it? And this is the structure of glyceraldehyde or dihydroxyacetone. So monosaccharides are the simplest carbohydrates. And under the monosaccharide, we have the trioses, let's start. Under monosaccharide, you have the trioses. The trioses are the ones that have 3 carbons. According to the calculation here, they have C3H6O3. Then we have the tetros. Tetros are those ones that have 4 carbons. So we have C4H8O4. Then we have the pentos, C5H10O5. And then we have the hexoses, C6H12O6. Under this is where you have glucose and fructose. So all these are the classification of monosaccharides. Okay. Now the next is disaccharides. Yes, that's everything about monosaccharides. Now let's talk about disaccharides. Disaccharides are, now in some cases, when you are giving the exam under monosaccharide, before we talk about disaccharide, they will say classify monosaccharide. The exam may just be classify monosaccharide. Now you use the classification of carbohydrates to classify monosaccharide. You say monosaccharide are classified into 2 according to functional group. Here you have what? Aldose and what? Pentose. Aldose and ketosis. Aldose is when it has the aldehyde functional group, and ketose when it has the ketone functional group. So that is one of the classification. Then according to number of carbons, now under the monosaccharide, you have, that is where you now have those trios, tetros, and the rest. All these ones, they fall under what? Monosaccharide. Yeah, they fall under monosaccharide. So please take note of that. You say classify monosaccharide, you classify this, you use this. Are you getting it? They are classified as either aldose or ketose. Is that understood? Now if they say classify carbohydrates, this is what you should classify: monosaccharide, disaccharide, oligosaccharide, and what? Polysaccharide. Is that understood? I just wanted to give you a brief. That is what I'm saying now, like a brief of what the carbohydrates are made up of. They are made up of aldose, made up of ketose, and the number of carbons. Is that understood? So all these ones now, like the ones that we'll be talking about, they are under monosaccharide: the aldose and the ketose, then the triose, tetros, pentose, hexose, pseudoheptose. All of them, they are under what? Monosaccharide. They are the simplest. Is that understood? Now let's talk about disaccharide. What are disaccharides or oligosaccharide? First, it's under oligosaccharide we have disaccharide. Now oligosaccharides are those carbohydrates that have 2 to 10 monosaccharide units on hydrolysis. All carbohydrate that yields 2 to 10 monosaccharide units on hydrolysis are disaccharide. All carbohydrate that use 2 to 10 monosaccharide units on hydrolysis are disaccharide. Oligosaccharide rather. They are oligosaccharide. Now, there is something that you need to know. They may ask, what are reducing sugars? All monosaccharides are reducing sugars. All monosaccharides are reducing sugars. Please take note. All monosaccharides are reducing sugars. So all monosaccharides are reducing sugars. Said all monosaccharides are reducing sugars. You should take note of that. And why are they reducing sugars? Now, as time goes on, we will understand why, but just note that all monosaccharides are reducing sugars. So let me keep you on suspense till that time. So that is that on monosaccharide. Like we are talking about oligosaccharides. We say they have 2 to 10 monosaccharide units on what? Hydrolysis. They yield 2 to 10 monosaccharide units on hydrolysis. Now, if they yield 2 monosaccharide units, what do you call them? Disaccharide. If they yield 2 monosaccharide units, what do you call them? Disaccharides. Is that okay? So if it has if you use 2 monosaccharide units on hydrolysis, you call them disaccharide. And the disaccharides are, we have maltose, then we have lactose, Then we have sucrose. Okay, all these are the disaccharide. Now, when two monosaccharides join together by glycosidic bond, two monosaccharides join together by glycosidic bond form a disaccharide. Now, when a disaccharide is hydrolyzed, hydrolyze means to what? Use water to break down something. That's why they call it what? Hydrolyze. Lysis. Two monosaccharides join by glycosidic bond to form disaccharide. Two monosaccharides join by glycosidic bond to form disaccharide. Then when a disaccharide is hydrolyzed, it gives rise to two monosaccharide subunits. Now, maltose comprises of glucose and what? Glucose. So when you join glucose and glucose together, it forms what? Maltose. Then lactose comprises of glucose plus galactose, or you can say galactose plus glucose. Then sucrose consists of glucose plus fructose. Now, we need to understand some things before we draw the structures of each of these carbohydrates. So, maltose, when it hydrolyzes, it gives glucose plus glucose. When lactose hydrolyzes, it gives glucose plus galactose. And then when sucrose hydrolyzes, it gives glucose plus fructose. So that is that for the disaccharides. Is that understood? That is that for the classification of the disaccharide. We are going to look at them in details later on. Now let us look at polysaccharides. Now polysaccharides are of two types. As name implies, poly means what? Many carbohydrates sub what? Units. When monomeric units rather, many monomeric units, when they join together like 50 and above, it forms what? A polysaccharide. 50 and above. Yes, like 50 and above monomeric units forms what? The polysaccharide. And they are classified into two. You have the homopolysaccharides, and then you have the heteropolysaccharide. We have the homopolysaccharide and heteropolysaccharide. Now, the heteropolysaccharides are also called the glycosamine glycan. Glycosamine glycan. Those are the heteropolysaccharide. Glycosamine glycan. Why the homopolysaccharides are called, they don't have a special name. But what distinguishes between the homopolysaccharides and the heteropolysaccharide? Now, we said there are many monomeric units, like 50 and above, joined together, it forms the polysaccharide. Now, homo means the same, while hetero means what? Different. So when the same monosaccharide unit join together, let's say glucose plus glucose plus glucose plus glucose, all of them, let's say the 50 combined monosaccharides that form these polysaccharides are all glucose, the same thing, all true. You say, when we say monosaccharide unit, we mean the monosaccharide like glucose, galactose, etc. Now, the question is, the polysaccharide, if it is only one monosaccharide that is present there, let's say only glucose, all true, that means 50 glucose came together, you call it what? Homopolysaccharide. An example is starch. And then you have starch, cellulose. All these ones, they are homopolysaccharide. Is that understood? So homopolysaccharides are polysaccharides that consist of one monomeric, one type of what? Monomer. That consists of one type of monosaccharide subunit. You can take it like that. They are polysaccharides that consist of just one type of polysaccharide subunit. Then we have the heteropolysaccharide. They consist of more than one type of carbohydrate subunits. And this is where you have the keratin sulfate. Keratin sulfate. We have the chondroitin sulfate. Something like this. Sulfate. We have the heparin. All these ones, they are heteropolysaccharides. So that is the classification of carbohydrates. We said they are classified as monosaccharide, oligosaccharide, and polysaccharide. Under the oligosaccharide, we have the disaccharide, which we are going to look in details later. Now let's talk about stereoisomerism in carbohydrate. Stereoisomerism in carbohydrate. Now, what is stereoisomers or stereoisomerism is a phenomenon whereby compounds have the same molecular formula but different 3D arrangement. They have the same molecular formula but different 3D arrangements. That's what stereoisomerism is all about, but different 3D arrangements or different spatial arrangements. Okay? That's what stereoisomerism is all about. Now, in order for us to understand stereoisomerism, we must understand what a chiral carbon center is. A chiral, or you can call it asymmetrical. It's either you call it chiral, asymmetrical, or stereogenic carbon center. Chiral, asymmetrical, or stereogenic carbon center. Now, a chiral or asymmetrical or stereogenic carbon center is a center that has 4 different groups around it. 4 different groups around it. For instance, if you look at this structure you have here that have 4 different groups, it mustn't be different functional groups. Any center that has 4 different groups around it is called a stereogenic or a chiral or asymmetrical center. Now, this chiral carbon center gives compounds their stereoisomeric properties. The chiral carbon center gives them their stereoisomeric properties. So let us talk about this for a chiral carbon center. Now let's look at the structure of the 2 basic carbohydrates, which are, you have dihydroxyacetone and glyceraldehyde. And let's talk about the number of stereoisomers that can be formed. Yes. We are talking about those ones, but let's talk about this. OH. Now, CH2. This is structure of dihydroxyacetone. Now, if they ask you for chiral carbon, you should be able to draw the structure of dihydroxyacetone to illustrate. Then let's look at, this is glyceraldehyde, and then this one is glyceraldehyde, and then this is dihydroxyacetone.
Where is it? Okay, that's glyceraldehyde.
This is glyceraldehyde, and this is dihydroxyacetone. Glyceraldehyde.
They are both examples.
Now, we want to see if they contain a chiral carbon. This is dihydroxyacetone. Let's see if this one contains a chiral carbon. A chiral carbon center is a carbon center with 4 different groups around it. So I may decide to take this H this way and put it here. And then here we have what? OH. Now, this carbon center here is called a chiral carbon center. Why? Because it has 4 different groups. If you look at it very well, you agree with me that this group here is different from this group, which is different from this group, which is different from this group. 4 different groups. So this is a chiral carbon center. Now, the number of stereoisomers that can be formed from a chiral carbon or from a particular compound is given by 2 raised to the power of n. The number of stereoisomers that can be formed from a given compound is given by 2 raised to the power of n. Here n is the chiral carbon. Here n is the number of chiral carbons. Okay, so in this case of glyceraldehyde that has 1 chiral carbon, it means n is equals to what? 1, and this will be 2 raised to the power of 1, and 2 raised to the power of 1 is equals to 2. It means that glyceraldehyde will have how many stereoisomers? It will have 2 stereoisomers. Now let's look at dihydroxyacetone. It does not have a chiral carbon. Why? If you take this carbon into cognizance, you agree with me that there is no fourth bond to make it to be how many? 4. So this does not have a chiral carbon center and hence does not have a stereoisomer. So let's take note of all these. Does not have chiral carbon. If you look at this is 1, 2, 3 only, and the bond is complete 5. There's no H here. If you add H here, it makes it to be how many? 5, and the valency of carbon is more than. If you add H here, it will now be how many? 1, 2, 3, 4, 5, and carbon must have a valency of how many? 4. Yeah, this is structure of dihydroxyacetone. So it does not have a chiral carbon center, no H there, double bond O. Now let's look at glucose and then see how many chiral carbons are present in glucose molecule, and then the number of stereoisomers that can be formed from glucose. Let's look at the structure of glucose and see the number of chiral carbon centers that can be formed from glucose. Now, this is the structure of glucose. You have C, double bond O, H, CH2, KOH, this is CHOH. Let me make it easier by drawing the fissure. This OH, H, C, here is what? OH, H, COH, H, COH, H, 1, 2, 3, 4, 5, and then finally CH2OH. Now the question is, how many chiral carbon center does this have? If you look at this very well, you agree with me that it has one chiral. This one is not a chiral carbon because it has how many groups around there? 1, 2, 3. This is not chiral. Now, if you look at this one is chiral. Why? Because this group here is considered as one. This group here is considered as one group. This group is considered as one. And then from here down like this is considered as one group. Are you getting it now? So in this case, we have 4 different groups because what is here is different from what is here. What is here is different from what you have here. All the 4 groups around these carbons are what? Different. So we can say that this is what? A chiral carbon center. So we have one chiral carbon center here. Is that understood? Now let's go to the next. If you also look at this one, now you discover that the group here is different from what you have here, right? And then everything that you have from here down here is different from everything you have up like this. Is that not so? So it has how many different groups around it? 4 different groups around it, and hence this carbon center here is what? A chiral carbon center. Is that understood? Now the same thing applicable to this. If you do it that same way, you get it that this one is different, this one is different. This entire group here is different from what you have up here. So this is chiral, and then finally this is H. Now if you look at this also, this is chiral. But if you look at this carbon, this is not chiral. Why? Because it has 2 hydrogens that are the same. Are you getting it? This is not chiral. If you want to bring it out, you say this is H, this is what? H, and this is what? OH. Since this hydrogen and this hydrogen are the same, you don't classify this one as what? Chiral. Is that understood? So in this case, how many chiral carbon centers do you have? The ones that are painted yellow are chiral. So we have 1, 2, 3, and what? 4. 4 chiral carbons. Now how do you represent it? You say 2 raised to the power of what? N, which is 2 raised to the power of 4. And 2 raised to the power of 4 will be what? 16. Is that understood? So it has 16 stereoisomers. Then if you want to talk about the enantiomer, it will not be 2 times 16, which will not be what? 32 in together. Because each stereoisomer has its own what? Enantiomer. Now, let's talk about epimers and enantiomers. And then from the idea of chiral carbons, now we can now talk about epimers and enantiomers. Now you'll be asked, what are enantiomers? What are enantiomers? Please. They are what? They are stereoisomers that are mirror images, non-superimposable mirror images of each other. They are stereoisomers. If you don't put that, you failed. Enantiomers are stereoisomers that are non-superimposable mirror images of each other. So you should take that. They are stereoisomers that are non-superimposable mirror images of each other. Are you getting it? They are stereoisomers that are non-superimposable mirror images of each other. Now, for something to be classified as an enantiomer, it must have a chiral carbon center. For instance, if they ask you to actually define what enantiomers are, I will advise that you draw a structure to show precisely the structure of either glyceraldehyde or glucose. So if I want to show now, let's say structure of glyceraldehyde, this is how it is. It's the simplest. You have this as OH, and this is what? Hydrogen. And this is what? C2OH. Now, while identifying enantiomers, you use the D and the L form. If the OH at the penultimate, that means second to last carbon is at the right hand side, it's the D isomer. Why if it is at the left hand side, it is the L isomer. So in this case, which of them is the second to last carbon? This carbon here.
This is right.
Yes, this right hand side.
Right hand.
Yes. Second to left carbon is this one. The OH here, is it at the right or at the left? It's at the right. So you say this is D-glyceraldehyde. D-glyceraldehyde. Is that understood? D-glyceraldehyde. Now the next one is L. Now what will be the difference between D and L? This is the point of reference. This other one now will be what? OH, and then H will come here. Now you can see the differences. This one, the OH is at the left hand side, while this is at the right hand side. They are mirror images. So you say this is L-glyceraldehyde. L-glyceraldehyde. So that is that for enantiomers. Now, you can use that of glucose also to explain the concept of enantiomers. They must be mirror images. If you use glucose, let's draw the structure of glucose and then draw the enantiomeric form of glucose. Let's draw the structure of glucose and then draw the enantiomeric form. Glucose is C double bond O, H, C O H, H. Then we have CH2. This C here, OH. This H, C, OH, H, C, OH, H, and then CH2, OH. Now, which of them is the penultimate? Second to last carbon, this is it. From top, 1, 2, 3, 4, 5. This is the second to last. Where is the OH? Is it at the right or at the left? It's at the right. So you call this D-glucose. And most of the glucose that are metabolized in our body is the D form of glucose, which is D-glucose. Now let's look at L-glucose. The difference is, see this double bond OH. Now, everything that is facing here, you carry them to face this way. So this one now will become what? This OH will come here. So you have OH here, you have H here. Then you have C. This OH will come here, you have H here. Is that understood? Now this other one now, you now have this OH facing here. That's why we call them mirror images. This other OH will be facing here, and then at the end of the day you have C2OH. So this is L-glucose. Structure of L-glucose. So that is all about enantiomers. Now the next one that we are going to look at are the epimers. What are epimers? Now epimers are stereoisomers. You must put that word.
Both of them are
They are stereoisomers. Epimers are stereoisomers that differs in configuration at only one carbon atom. That differs in configuration at only one carbon. That differs in configuration at only one carbon. Now, galactose and mannose. Galactose and mannose are C4 or C2. Mannose are C2.
Galactose are C2.
Galactose and mannose are C2 and C4 epimers of glucose. Galactose and mannose are C2 and C4 epimers of glucose. They are C2 and C4. That means mannose differs from glucose at only position number what? 4. Position number 2 rather. Position number.
Is at 4.
I said galactose. I started with galactose. Galactose and mannose rather. Sorry. Galactose and mannose are C2 and what? C4 epimer of glucose. It means galactose differ from glucose at position number what? 2. While mannose differ from glucose at position number what? 4.
This place, is it?
Yes. So if I want to draw the structure of mannose now, what do I need to do? Just change this position. Take this OH to this side and then take this one to this side. It gives you the structure of what? Galactose. So that is the only difference between galactose and glucose.
I'm gonna drink now. Are you guys shy?
Or what am I saying? It's supposed to be mannose. Mannose, yes. I missed it.
Galactose is 4, okay?
Yes. Mannose and galactose. Sorry. Mannose and galactose are C2 and C4 epimers of glucose. Mannose and galactose are C2 and C4 epimers of glucose. So if I want to draw the structure of mannose, just draw the structure of glucose first and then change the configuration at position number what? 2. Is that understood? Change the orientation of the OH at position number 2. So yes. So this one now, if I want to draw the structure of mannose, it will be C double bond O, then H. Here's position number 4. This one will now be what? OH here. Are you getting it? And here will be what? H. And then here will be C. Here will be what? OH. And what? H. And then C. OH. H. C. OH. H. And then what? C2 what? OH. Is that understood? Now, that of galactose now will be what? This is for mannose. This for mannose. That for galactose will be what? Change the position at position number what? Change the OH at position number 4. The orientation. So this is 1. Here is what? 2, 3, and what? 4. At position number 4, just change the orientation. Let here be OH, and here is what? H. Is that understood? It will give you the structure of galactose. So this is not galactose. This is mannose, and this is what? Glucose. D. This is galactose. Are you getting it? This is what? Mannose. If you want to talk about glucose, D-glucose, not L-glucose. Everything we are drawing now is D-galactose, D-mannose, and then what? D.
They can still be D. They can be L-mannose too.
Yes.
I'll just change the penultimate.
Yeah. You just change the penultimate.
It will be full next.
Eh? So that is that for the stereoisomer, the epimers. So let's talk about the optical isomers. Now, optical isomerism is when these enantiomers having the D and L form, or let's say a compound with a chiral carbon center is a solution of it.
Enantiomers having the D and E.
And that's enantiomers now.
Hey.
When they are placed in, when a light is passed through a solution of such compounds having a chiral carbon center, when plane polarized light is passed through a solution having a chiral carbon center,
It's passed through.
when plane polarized light is passed through a solution of enantiomers, or let's say a solution having a chiral carbon center, are you getting it? When it's passed through a solution of enantiomers, it rotates the light either to the right or what? To the left. It rotates the light either to the right or what? To the left. Or left. Okay? to rotate light either to the right or left. Now, if it rotates the light to right, you call it dextro-rotatory. Is that understood? Dextro-rotatory. Dextro-rotatory. Now, if the light is rotated to the left, it's called what? Levo-rotatory. Now, something that you must know is dextro-rotatory and levo-rotatory has nothing to do with D and L isomer. So, an isomer now, the enantiomer can be the D form and it can be what? Levo-rotatory. Is that understood? What I mean by that statement is the D and L form has nothing to do with whether it will rotate to the right or to the what? Left. Are you getting it? Some cases, some persons think, okay, because it's D isomer, it should be what? Dextro-rotatory. Do you understand that?
They say if it rotates to the right, it's dextro. If it rotates to the L, it's left.
That's what I'm saying now. Seriously?
What are you doing?
Okay. What I'm saying is dextro-rotatory is when it rotates to the right, and levo-rotatory is when it rotates to the what? To the left. Now, I said the dextro-rotatory and the levo-rotatory has nothing to do with D and L. You know, D isomer is when the something is at the what? Right. Are we getting it? When the OH at the penultimate is at the right. Why the L isomer is when it is at the what? Left. So some persons will be like, since right, it should must be what? Dextro-rotatory. Do you get it now? So a compound can be dextro-rotatory and be what? D isomer. And it can be dextro-rotatory and also be what? L isomer. So D and L, no, the D and L isomer has nothing to do with what? Dextro-rotatory or levo-rotatory. So we can have, let's say, L, then what? Positive. Positive most cases means what? Dextro-rotatory. Are you getting it? Why negative means what? Levo-rotatory. So we can have L dextro-rotatory or what? D levo-rotatory. Are you getting it now? So that is that. Now mutarotation. Now at some point the specific rotation would be around, let's say, 12. Why the other one would be around, let's say, 70 something.
I mean,
road level will be in the solution. Are we getting it? Now, before we talk about this, we'll talk about alpha and beta. Let's talk about that one first before we come here.
But you say mutarotation.
Mutarotation. I have to talk about the alpha and beta form of glucose. Now, let's talk about anomers. What are anomeric carbons? What are anomers? Now, disaccharide that occurs between carbon 1 of glucose and carbon 5 forms hemiacetal and what? Hemiketals, depending on if it is ketone. Okay, forms hemiacetal for aldehyde, and then for ketone, it is between carbon 2 and carbon 5. This one form hemiacetals.
The same hemiacetal.
There's difference. This one is aketa, hemiaketa.
Is this C2-5 or C and?
This C1 to C5 for this. For aldose, which is glucose. Are you getting it?
C1, not C1 and 5.
C1 to C5. Disaccharide between C1 and what? C5. Why this other one is between C2 and C5 for what? Glucose. Leads to the formation of two structures, which are what? The pyranose structure. Pyranose is six-membered ring, and then we have furanose. Furanose is 5-membered ring. Are you getting it? So it forms this. Now, this anomeric carbon, that carbon where the cyclization occur is what is called the anomeric carbon. In the for glucose is C1. Are you getting it? For glucose is what? C1. And then for fructose is C2. And the orientation that is formed are two. We have the alpha anomers. Around the configuration, we have the alpha anomers. And then we have the beta anomers. So if I have the structure of glucose, what is glucose? C double bond what? O. H. Abi? Then we have C. What are we going to have here?
OH.
OH. And here is what? H. And here is what? C. OH. And here is what? H. And here is what? C. COH. And here is what? H. And here is what? C. OH. And here is what? H. And finally, what do you have here? CH2OH. Now, that cyclization for glucose occur between this carbon and what? This carbon. Are you getting it now? Now, this will now lead to the formation of something like this. Listen. To now lead, these two, they will cyclize, and then it will now lead to the formation of this. Cyclization to now lead to the formation of this. To lead to the formation of this. Now, what will now be the structure? It will form a pyranose structure. Now, there are two configurations around the anomeric carbon. The anomeric carbon, in this case now, is the carbon 1 for glucose. Are you getting it? There are two configurations, which is the alpha anomer and the what? Beta anomer. Are you getting it? So let us know the alpha anomer and the beta anomer. Now, the structure is something like this. You form O. This is where this oxygen is. The cyclization leads to this.
This oxygen?
Yes. Then you now have something like this. Please take note of what I'm doing. Now, assume you turn this thing upside down. What can you see?
Turn it upside down.
Assuming
H.
you turn this thing upside down, what can you see? Here, OH should be here.
OH should be there. Really?
Yes, OH should be here.
Why?
Let me show you how it is. It's just like you have normally something like this. C double bond O. This aldehyde functional group, Abi. H, Abi. And then you have something here. This normal aldehyde functional group. Is that not so?
Yes.
Now, it continues like that. Then we now have this O coming from here. It has what? This O here, it has oxygen. The OH from this, it has what? Oxygen. Are you getting it? And this oxygen has what? Lone pairs of electrons. I don't want to teach you chemistry. What happened is this one will come here. Is that not so?
So I mean, man just no safe for any of those. OH they did them.
Yeah. So nobody will even ask you that. It's just the structure, the alpha anomer and the beta anomer that you need to draw. So now in this case, this carbon here is what is called carbon 1. This OH here, listen oh, if this OH is up, you call it beta anomer. Now, after OH, what do you have here? H, right?
After this OH, right?
After this OH is this H now. Then, listen, you will come use your eye now. Turn this thing upside down. Me at the video, but I have to speak pidgin English for you to understand this better. Carry this thing like, let this base be sitting on the ground. Visualize it like that. If this base is sitting on the ground, it means here will be what?
H.
Here will be what?
H.
Here is what? H. And here will be what? OH. Then here will be what?
OH.
H. And here is what? OH. Abi?
Yes.
Then which other? This one will be what? OH. And here will be what? H. Are we getting it? And then this carbon now.
That's the fifth carbon.
This is the fifth carbon now. Now this carbon, what is attached here?
H.
No, that will be H here. Then you now this H here now. This is the carbon now.
Why is it coming down? It's supposed to be up now. Just so we turn like this.
That is what I'm telling you. This OH, this C2OH can still face this side. You understand? This orientation, at this position, you don't mind this whole thing again. Okay. This C2OH must be what is on top here.
Even for the other.
Yes.
For
Furanus. This C2OH must be what will be on.
I think I've seen the structure when H used to be up.
No. This one has to be like this. So this is the structure of what? Glucose. Are you getting it now? Now this one, what do you call it? Beta D glucose. Are you getting it? You call this what? Beta.
Well, my confusion before in Mila was that is this OH and H, where is it coming from? I never knew that it was this. There was OH here.
It's from here. Are you getting it now?
Yes.
So this beta D glucose. Is that understood? That is beta
But
D
the OH is
glucose.
up.
Yes.
If the OH has been down.
If the OH is down, let's say you have H here and this OH is down, you call it alpha D glucose.
What will make the OH down? Emila.
What will make the OH is the orientation. That is why you call it stereochemistry. That means if this H is somewhere around here,
What will make it there?
that is stereochemistry. It's not something you can visualize with your eye. Are you getting it? They are just telling you that if it is like this, HOH is the alpha form. Why if this OH is on top, is what? Beta form. That's stereochemistry for you. It's not something that you can do on the board and they say this is why it's like this, now why it's like this. The formation in the body. Are you getting it? It's just like we human beings. Normally, human beings, how do we human beings walk? We walk with our leg now. That is how God has made it. So you now say when human being is walking with the leg, what do we say? It's normal walking, right? How about if the person is walking with his hand or head? You now say it's abnormal. Are you getting it? That is how it is here. So this is structure of what? Glucose. Beta D glucose.
Okay.
This alpha D. This beta. Why? Because the OH is what? On top. Now, if the OH is down, what would you call it?
The OH is down.
Down.
Beta. It's alpha. No?
Alpha. Is that understood down? So from here now, we cannot go straight to disaccharides. So you now understand what anomerism is, the cyclization that gives rise to two isomers, the beta form and the what? Alpha form. Is that understood? So if they ask you, you should be able to explain and draw the structure at least to explain. Now, having known this, we are now coming straight now to disaccharides. Now, disaccharides are formed when two monosaccharides are joined together by glycosidic bond. Are you getting it? By glycosidic bond. Now listen, how is a glycosidic bond? Glycosidic bond is oxygen bond. Glycosidic bond is what? Oxygen bond. Like 2OH, they react in such a way that water molecule will be what? Eliminated. Is that understood? When this alcohol group and this alcohol group react, water molecule will be what? Eliminated. If water molecule is eliminated, what are we expected to form? Is it not something like this? Because OH and one H will leave to form what? H2O. So what is left is what? Oxygen. Is that understood? So this linkage is what is called glycosidic linkage.
I mean, this thing is eta.
This eta now, the functional group, but the bond is called the glycosidic linkage or oxygen linkage. You can write it anyhow you want to do. Now, having known this, we are now coming to disaccharide. Let us draw the structure of maltose. What did I say for maltose? Is what? Glucose plus glucose. Now, you need to know the formation of maltose. What part of the glucose reacted? Maltose. Maltose is glucose plus glucose joined together by alpha 1,4 glycosidic linkage. They are joined together by what? Alpha 1,4 glycosidic linkage. This is the only thing you need to remember for the exam because you know the structure of glucose now. Alpha 1,4 glycosidic linkage. It means carbon 1 of glucose and carbon 4 as of another word, glucose. But the two glucose, carbon 1 of one glucose joined together with
carbon 1 of this glucose.
Of one glucose. There are two glucose now. So we say carbon 1 of this one plus carbon 4 of this other glucose.
And it's alpha. That means that one, the OH should be down.
Down for both of them. Are you getting it now?
I can't draw the two different.
You draw the two structures. Different. Look at this one. Yes. So this is alpha. And then you form something like this. This is what? CH2OH. And then you form this H. This. And then you have this. And then you have this. Now you have the OH
all these
here.
All to change, Mila. All these H and OH, they're always there.
They're always there like that for glucose. So we have, for this one, this group is here. This group here is what? OH. And here is what? H. And here is what? H. What do we have here? OH. The last one, what do we have here? For this one? OH. And here is what? H. Is that not so? This one now is
glucose. How do you call it?
This one is alpha D glucose normally.
This is normal alpha glucose. Then for this 4, how will it not be now?
Now you now draw another glucose like this. Look at what I'm doing now. Where is the carbon 1? This carbon 1, this carbon 2, this carbon what? 3, this carbon what? 4. So this other side now is now what we react with this side of this one. So if I want to draw this now, it means that I will start my drawing from here. Then it will be this. And then you have something like this. What do we have here? Here will be what? OH.
Okay, this time I'm not going to start from the 4.
Yes, OH. And here will be what? C2, OH. And here will be what? H. Here will be what? OH. And what? H. Here is what? H and OH. And then here is OH and H. This will not be the structure. Do you understand now?
It's not the same thing.
It's the same thing. This is also glucose.
But what's the difference between 1 and 4?
This alpha D glucose. This alpha D glucose. Now, what is the difference between 1 and 4? See the difference here. This one here is what? Carbon 1. Here is what? Carbon 2. Here is carbon 3. Here is what? Carbon 4. So it means we are joining the carbon 1 of this glucose to carbon 4. That is where you have the 1, 4.
Oh, now yeah, that thing go come like this.
Yeah. You understand it now. So this is why they call it alpha 1,4 glycosidic linkage. Do you understand now? So these two now, when they react, according to what I said, when two OH react, what will be formed? To form just oxygen bond in the middle, right? So we remove this OH and this OH here, and then what do we have here as a linkage? Oxygen. Is that understood? So this is the structure of maltose. You now understand it, right? This is the structure of maltose.
Allow me to write. Yeah. I still get a lot of this. See when they be like this. Oh, God, this.
Now let us look at the next one.
I write.
Maltose is beta 1,4 then glycosidic linkage between galactose and what? And glucose. Between galactose and glucose. That is lactose. Are you getting it? If I want to rewrite it now, let's say lactose is what? Let's say carbon 1 of galactose. Which kind of galactose? Beta galactose. Are you getting it? Plus carbon 4 of what? Beta D glucose.
Galactose is coming first.
Yes, galactose is coming first. Now galactose is what epimer of glucose? C2 or C4? C4. So you are now going to come here, draw the structure of glucose again. This is the structure of glucose here, which is O. What do we have here? This. Now, it's beta. So this OH should be what? On top. Are you getting it? And this one will be what? Under. Is that understood? Now, every other thing still remains. This OH will be here. Okay, OH is done for the first one. Think so, yeah. Then for this one, OH is what? On top. H. And then for this one, it is under. And this, you have C2OH. Now, this is the structure of glucose normally. But at position number 4, galactose, the difference between galactose and glucose is at position number 4, there is change. So this is 1, 2, 3, 4. So what do we do here? We take this OH up and then bring this one down. Is that not so? So that is the structure of galactose. Now, this will form a linkage with glucose. Now, the structure of glucose is this. Beta D glucose. Now, what do you think will be the structure of beta D glucose? The OH will still be under or on top? On top. Then you have hydrogen here. Then you have H, OH. Now you have OH, H. Here's what? OH and what? H. And then you have what? C2, OH, and H. What do you have between these two like this? A linkage, right? Because I say when OH and OH react, this one will cause here.
So yeah, we'll clean off.
So you have this bond coming here to react with this one. This one will no longer be here. Then you form here. So this is the linkage. 1, 4, beta D linkage. Are we getting it? Beta D linkage. Or you can say 1 beta galactose, 4 beta glucose linkage. Are you getting it now? Glucose linkage. So that is the one for lactose. Now, if you look at these ones, listen, this here reducing sugar now comes into play. Are you getting it? This here reducing sugar now come into play. Now look at these ones very well and see if they are reducing sugar. Are they reducing sugar? Now, reducing sugar are the ones that have free OH. You draw it, don't worry. Reducing sugar are the ones that have free OH. Is that understood? Free OH at the anomer carbon, which is carbon 1. Are we getting it? So if it has free OH at the anomeric carbon, in terms of glucose is carbon 1, you call it is what? Reducing sugars. Are you getting it now? Free OH, it means this OH is not linked to another group. Okay. So this one is what? Reducing. Okay. Are you getting it now? That's why I said all monosaccharides are what? Reducing. Now, look at this one. Is it reducing or not reducing? Does it have free OH here? Yes. This OH isn't linked to anyone. So this one is what? Reducing sugar. It's reducing sugar. Yes. Sucrose is what? What are the two units that comprise of sucrose? The two monomeric units of sucrose is what? Is D-glucose, alpha D-glucose, and beta D-fructose. And the linkage is 1 to 2. Alpha D-glucose and beta D-fructose. With a linkage, I said sucrose.
The sucrose we are now done with everything.
Yes, sucrose, we have alpha D glucose, the linkage, plus what? Beta D fructose. At carbon number what? 1 to 2. That is where they link together. Now let's draw the structure of alpha D glucose. Alpha D glucose is what? What is the difference between alpha D glucose and beta? Alpha is the one that have the OH under, right? Yeah. So alpha D glucose is something like this. You have OH, and here is what? H. Abi? Then you have what? What are we going to have here? Is this H or OH? OH here. H. Then this is what? H. And here is what? OH. And here is what? OH. H. And then here is C2, OH, and H. This is what? Alpha D glucose. Okay? Now, where is beta D fructose? The structure of fructose is a furanous structure. Furanous is something like this. 5. 5 carbon chain. You have it like this. Then here you have OH. And then here you have OH. Here is H. Here is H. And then on top here you have H, and here is C2OH, and then here you have OH, and then you have still the same thing as C. You can say CH2OH or CH2OH like this. Now this is the structure of fructose. Now the question is, which of them is carbon 2? Which of them is the anomeric carbon for fructose? Now this is the anomeric carbon. Are you getting it? This carbon center here is what? Anomeric.
That's
Carbon 2, yes. Are you getting it?
I thought you cancel like this one.
No, the structure normally is supposed to be like this. But because of the reaction, that's why I drew it like that, because it will react with what? Carbon 4 of that one. Carbon to react with carbon 1 of this one. So carbon 2 will react with carbon 1. Normally it's supposed to be this way. What do you have here? OH, right? Normally, you'd have the OH. The OH is the one that tells you where the this will be. Then what do you have here? CH2OH. Is that not so? This fructose, this is the structure of fructose I'm drawing now. Then after this one, now what do you have here? You have OH, and here is what? H, and then you have what? OH, and here is what? H, and then here, what do you have? you now have H and CH2OH. This is structure of fructose normally. But because carbon 1 and 2, carbon 1 of this is reacting and carbon 2 of this are coming together, what are we now going to do now? We now have to draw it in such a way that this part now will face this side. Do you understand? Like this part here, we have to face this side. That is why we have it at this position here. This is the carbon 2. Is that understood? So we turn this structure now, like flipped it aside to give what we have here. Is that understood? Now what we now do now is when these two come together, what will be formed? To form a glycosidic linkage, right? Abina. There's OH here now. When two OH react, water will be given off, right? To now form a glycosidic linkage, which is O and what? O. So that is everything you need to know about the structures. Now, another thing that you need to read, prepare well for your exam is, another thing that you need to prepare for is the biological importance or the biomedical importance of what? Of each of these disaccharides. It's something that you should read. Biomedical importance of fructose, biomedical importance of lactose. Then we have maltose and sucrose. You should know the biomedical importance. And then you should know what lactose intolerance is. Inability to completely digest lactose. Lactose intolerance. Inability to digest lactose, which can lead to bloating. Like you feel as if you are not hungry, or you've not eaten. It's just as if air is filled up in your stomach, like your belly na air full am. That is what is called lactose intolerance. And one of the symptoms is bloating, and then sometimes you'll be diarrhea, light diarrhea and bloating. So that is lactose intolerance. Inability to what? Digest lactose fully is a medical disease or disorder associated with lactose. Please take note of that. So those are the structures of all the disaccharides. Now let us talk about the polysaccharides. Let's talk about polysaccharide. Yes, polysaccharide, the structures of polysaccharides. Now, under polysaccharide, we say we have two classifications under polysaccharide. We have homo polysaccharides. We have the homopolysaccharides and then you have the heteropolysaccharide. Now the heteropolysaccharide are also called the we have the not heteroglycan, we have the glycosamine glycan. Under here you also have the mucopolysaccharides. Okay, glycosamine glycan, and then we also have the mucopolysaccharide. For instance, starch. Then we have other examples, cellulose. All those ones, they are homopolysaccharide. Then heteropolysaccharide, when you hydrolyze them, they yield a mixture of different monosaccharide. So when different monosaccharide join together, they form heteropolysaccharide. And when you hydrolyze them, they yield a mixture of different monosaccharide. What I mean by that is, hydrolysis means what? To break down. So when these heteropolysaccharides are broken down, they don't form only one monosaccharide. Maybe in this heteropolysaccharide, you may have glucose, you can have fructose, you can have others, you can have galactose. Different one upon hydrolysis yield different monosaccharide that called what? Heteropolysaccharide. So Let us draw the structure of mucopolysaccharides. Mucopolysaccharide.
Glycolysis means to break down, be
Hydrolysis means to break down. Let us look at mucopolysaccharides. Now, mucopolysaccharides are heteroglycans made up of repeating unit of sugar derivative. Made up of repeating units of sugar derivative. Repeating units of sugar derivative. They are the ones called the glycosamine glycans. Are you getting it? Yes, the mucopolysaccharides are the ones called glycosamine glycan. They are called glycosamine glycan. Now, example is hyaluronic acid. Hyaluronic acid. Let me just draw the structures of each of them. Hyaluronic acid. Now, since they are polysaccharide, you use brackets to indicate them. Hyaluronic acid. Please take note. This was the test questions. No, hyaluronic acid is a separate one of its own. Now, hyaluronic acid contains glucuronic acid. That means glucose that has been oxidized. Glucuronic acid. It contains glucuronic acid plus N-acetyl glucosamine. N-acetyl glucosamine. N-acetyl glucosamine. This is hyaluronic acid. Now, what will be the structure of hyaluronic acid? It's something like this. You have your normal glucose. Please take note of this. These are the test questions. Yes, so these are the test questions. You have H here. You have OH. You have H. You have what? OH. Then you have H. Then you have oxygen here. This oxygen now is what is linked, because these are repeating unit of this. So you put this outside to show to you that this thing continues like that. Now, this is like the structure of glucose. What is the difference? This alcohol here has been oxidized to give us acid. So you have glucuronic acid. And then you now have your hydrogen. So this is beta D glucose or beta D glucuronic acid. Then it's linked again to another group entirely. We have something like this. Now this one continues, and then it forms hydrogen here, and then you have your OH, and then you have hydrogen here, then you have hydrogen here. Sorry, here is supposed to be CH2OH and then H, and then you now have the N-acetyl. This acetyl group, CO, CH3, then here is bracket N, and then you have hydrogen, and then this linkage continue. So this is the structure of hyaluronic acid. You should take note of all these structure. Now, what I will do now is to just draw the structures and then show them to you. To draw the structures, just copy them from the internet and then draw, because it's something that we have to memorize. There's no two ways. There's no way that somebody will show it to you that this is how to draw it or whatsoever. So I will just try and draw each of the short structures and then show them to you. So that will be the end for this. Another thing again, that you should know what distereoisomers are. Distereoisomers. The stereoisomers are stereoisomers that differs in only the position of what? One of the groups only. They are like epimers too. Like epimers. So that will be the end for this, okay? On
Are they the same as
carbohydrates.
Epimers?
No, they are not the same.
Why?
They are different.